welcome again to the new lecture on the course properties of materials. So, let us just briefly see what we did in the last lecture. So, in the last lecture we saw introduction to microscopic mechanism of basically plastic deformation. We saw that if you do characterization of the materials after plastic deformation, one can see that materials crystal structure lattice parameter and volume remains constant. So, this can be found out by detailed characterization. Now, if that is true, then what is that which leads to plastic deformation? And it turns out that it is a phenomena called as, so microscopic phenomena, one is called as slip, in which the plane of atoms in one part of the crystal slip against the other part of the crystal. So, across a plane called as slip plane, leading to movement of atoms against each other. So, this happens on certain planes called as slip planes, and it happens along certain directions, atomic directions called as slip directions, and we will see details of this in today's lecture. And then second phenomena is less common. So, this is the most common. Second is twinning, twin related deformation, which is basically formation of twins and deformation caused by it, but generally this is less common, and mostly it happens at low temperature when slip is not active or slip systems are not active. So, we will in this course we will mostly discuss about the slip, we will not talk about the twins as such. So, let us see what this slip is. What is slip induced plastic deformation? So, generally atomically speaking, slip happens on certain, it happens on certain crystallographic planes only, and along certain crystallographic directions. So, this together, so these are called as slip planes and these are called as slip directions, and basically it happens in this fashion because they lead to lower value of required stress to deform. Okay, there are theories behind this, microscopic theories, but essentially it is because of lower value of stress that is required to deform the material. So, together they make what we call a slip system. So, a slip system contains slip planes and slip direction. Okay. So, slip system is a combination of slip plane and slip direction. So, naturally the slip direction lies in the slip plane. I mean, you cannot have one plane and another direction. The direction has to lie within the slip plane. So, this is first condition. So, that means if slip direction is UVW and plane is HKL type, then dot product of UVW to HKL is equal to 0, basically means UH plus Vk plus Wl is equal to 0. So, if you have 1 1 1 plane as slip plane, let us say, then the only directions which can slip, which can give rise to slip are, so 1 1 1 will make dot product 0 u v w. So, essentially u plus v plus w has to be equal to 0. So, which means it could be 1 bar 1 0 direction, it could be bar 1 0 1 direction, it could be 1 1 bar 2 direction, bar 1 2 direction, and so on and so forth. So, what determines along these directions which will be the direction? So, the next thing is slip direction is a closed packed direction. So, it is the direction along which atoms touch. So, you may have a direction in which atoms are touching each other, you may have a direction along which atoms are not touching each other. So, this is not the slip direction, this is the slip direction, which is the closed packed direction. Okay. So, slip direction is a closed packed direction. In majority of the cases, slip plane is also a closed packed plane, but this is only possible for closed packed systems. So, if you look at systems like FCC or HCP, they have closed packed, they are closed packed structures, and as a result they have closed packed planes. Okay. So, the question is, why is that slip planes are usually closed packed? Why is that? So, closed packed plane, why closed packed direction, why. So, this is slip plane, this is slip direction, and this is because the closed packed planes have the stress required to move atoms in them is smaller. So, let us see first what closed packed, how do you work out what is a closed packed plane, what is not a closed packed plane, before we come to this in little bit more detail. So, let us first look at how do you determine a plane is closed packed. So, let us say we work out what we call as planar density in planes in crystals. So, basically planar density, or we can say PD, PD is given as number of atoms on a given plane divided by area of the plane. So, basically number of atoms per unit area. So, let us say if we want to calculate PD on 110 plane of FCC crystal. So, first we do is that we make a, let us say, a cube, let us say these are the atoms that we have. So, the 110 plane is the plane which is this plane. All right. So, how many are the number of atoms? So, in this plane we can see the number of atoms are, so this is 1/4, this is 1/4, this is half, this is half, this is half. So, these two are half, these two are 1/4. So, total number of atoms is basically you can say 4 by 4 plus 2 by 2, this is 2 within this area. And what is the area? If the atomic radius is r, so you can see that this is basically you can say a, this is a root 2. So, this is a into a root 2, which is root 2a square, and in FCC we know that a is equal to 2 root 2 r, where r is the radius of atom. This will work out to be 8 into root 2 r square. So, planar density can be 2 divided by 8 into square root 2 r square. This will be essentially 1 divided by 4 into root 2 r square. So, this is how you can find out the planar densities, and it turns out, now if you do the maths, then for let us say for BCC, if you take the primary planes, so let us say along 100, the planar density is 1 divided by a square. So, let us say we write in terms of a. So, I mean you can write this in terms of a as well. So, in terms of a it will be 2 divided by square root 2 a square, or square root 2 divided by a square. So, this will be this, and 110 will have a planar density of 2 divided by square root 2 a square, and this along 111 it will be 1 by square root 3 a naught a square. Okay. And out of these 3 you can see the maximum density plane is, this is the highest density plane 110, but this is not a closest packed plane, but it has the highest density. Closed packed planes means the planes in which atoms touch each other, these are the closed packed planes. So, this is not a closed packed plane, but it does have a closed packed direction. So, if you look at BCC crystal, so you have an atom sitting here, you have another atom sitting here, so this atom and this atom, they touch each other. So, you can say that a root 3 will be equal to 4r, this is the relation. So, 110, this is, so this 110 plane itself is not a closed packed plane, but it is the plane with highest density. All the planes are going to be smaller density, but it has a closed packed direction, but has a closed packed direction. And you can work this direction out. This direction from here to here is a 111 type direction. So, basically 110 plane will have 111 type of direction. So, of course, the dot product has to be 0. So, essentially it could be bar 111 type of direction. So, there could be multiple combinations. So, this will make a slip system in BCC. So, 110 plane is the highest density plane. So, 110 is the slip plane. Coming to FCC, okay. So, FCC is this, where you have this atom, this atom, this atom, this atom and this atom. Okay. So, essentially you can say that the atoms touch along the faces. Okay. So, So, atoms touch along 110 directions, and there is a plane which is this plane, which is 111 sorry, which is the plane in which atoms touch each other. So, essentially 111 plane will look something like this. So, let me see if I can draw it correctly, like this, something like this. This will be the 111 plane, all right. And if you now calculate the atomic density for different planes, for 100, for 110, for 111, this will be 2 divided by a square, this will be 2 divided by root 2 a square, this will be 4 divided by root 3 a square. So, this has the highest atomic density and it is the closest packed plane. This is how you work out the planar density. For a direction you can work out linear density. So, let us say you have a FCC, again you go to FCC. So, linear density you can define as number of atoms along a vector divided by length. So, basically number of atoms per unit length. So, let us say we want to calculate numbers. So, we want to calculate LD along 110 for FCC. So, for FCC we know that number of atoms. So, if you go to previous picture, this is the direction 110. So, if you take along this AB, so along AB number of atoms is equal to you can say 2, right, and length along length of AB is equal to 4 r or a root 2. Okay. So, LD along 110 for FCC will be equal to 2 divided by 4 r or 1 divided by 2 r. You can also show LD along 100 and 100 will be square root 2 divided by 4 r. I will leave it to you as a homework. So, it turns out that basically you can find out using linear density what is the density of atoms along a particular vector, and you can find out the planar density. So, essentially slip takes place on the planes along the directions along which linear density is the highest. So, slip directions are highest linear density directions. So, they happen to be closed packed directions. So, if you look at the cases of FCC, BCC, HCP, simple cubic, these are all, they will have closed packed directions, atoms assuming that touching a sphere model. And then slip planes are highest planar density planes and or you can say closed packed planes. Closed packed planes are not present in all the crystal systems. So, only for HCP or FCC, because that is where you form closed packed planes. For BCC and HCP, for BCC and simple cubic we are looking at planes which have highest crystal density. So, essentially these are slip planes. The combination of two, as we said, is slip system, but with the condition that UVW lies in HKL. So, UVW dot HKL is equal to 0. So, this is what the definition of slip system is. So, now let us see, we work out the slip system for FCC. So, slip systems in FCC. So, we have atoms, we do not make touching atoms just to for the sake of clarity. Okay. Now, we know that highest density plane is this plane. So, this A, B, C is the 111 plane. How many 110 type of directions lie in this? So, it turns out, so we saw that for FCC closest packed plane is 111 type and closest packed direction from the calculations is 110 type. Okay. So, let us find out different combinations. So, we can see that in this 111 plane, if this is x, this is y, this is z. In this plane there are 3 110 directions, one is this, second is that, third is this. What are these directions? So, 110, 111, so basically you can say 111 dot UVW is equal to 0. So, you can say that U plus V plus W is equal to 0, and we know that these directions are only of 110 type. So, ignoring all other combinations, it will lead to bar 101, 10 bar 1, which are identical, just opposite, bar 110 or 1 bar 10 and then 0 bar 11, 0 1 bar 1. So, basically you can see that one plane can contain 3 directions. So, basically you can have total of 3 slip possibilities. Slip can occur along 3 different directions. So, these are 3 slip systems. So, likewise in a FCC crystal you may have multiple 111 planes. So, this is one 111 plane, the second 111 plane is this. So, let us use different color. This is another 111 plane. You can have one more plane, that is let us say this. Okay. If you connect this, this and that, let me use different color, maybe 1, 2 and 3, and the fourth one could be. So, you have, so let us write the combination. So, you have 111, you have bar 111, you have 1 bar 11 and you have 1 1 bar 1. You can write other combinations as well. So, essentially for this bar 111 will be 1 bar 1 1, for this it would be bar 1 bar 1 1. So, these are opposite planes basically you can say, and for this it would be bar 1 bar 1 bar 1. So, you have multiple 8 possibilities because you have 8 vertices, but 4 of them are, 2 of them are equivalent. So, as a result you will have total of 4 planes. So, 4 111 type planes. I will leave it to you as a homework. Draw these planes and find out the directions and make a list. of slip systems. So, 4 111 type plane into 3 direction in each plane, this gives you 12 slip systems. So, in a general sense you can say you have 111 plane as slip plane, direction is 110, this is slip system. Of course, you have to choose combination for which direction lies within the plane, that is the dot product of the two is equal to 0. So, that is what you have to do, alright. So, similarly you can do this work for BCC as well. So, we do not have time for that today, we will do that in the next class. I will leave it to you to do some homework in this direction before we take up this in the next class. So, what we have done in this lecture is basically we have looked at, we have invoked the concept of slip systems. So, a slip system consists of two entities, one is slip plane and the slip direction. Slip plane is the plane on which the planar density is highest. In case of closed packed system, it is the closed packed plane. So, for FCC it is 111 type of plane, for HCP it is 0001 type of plane, but BCC and simple cubic structures do not have a closed packed plane. So, in that case the highest density plane is the slip plane, and the closed packed and the slip directions are directions which are closed packed directions or directions with highest linear density. So, in all these systems we have directions which are closed packed, that is along which the atoms touch each other. So, for one FCC the direction is 110, for BCC the direction is 111 type, for simple cubic it will be 100 type of direction, and for HCP it would be one of those in plane directions of 100 or 01 kind of directions. So, we will do some more analysis on the slip systems in the next class to find out BCC and HCP slip systems before we move on further. So, thank you very much.